All right, so today we're going to talk about section 6.6 vectors. So, in terms of vectors, this is kind of a new topic for us in this because we've been kind of talking about it in terms of just line segments and everything. So, now we're going to have to talk more about directed line segments and everything in order to get to our vectors and all of our different components. So quantities that involve both a magnitude and a direction are called vector quantities, or short, we just call them vectors. Scalars are numbers that you multiply vectors by, and the length of the directed line segment is known as its magnitude. So in all cases, we're going to have something we're going to identify the initial point and our terminal point. That way we know where we started and where we end in every time that we do something. So every time it's always going to say from point P to Q, or it may list it something like this right here. This identifies it as the vector PQ that we start at P, we end at Q. So we got several different things that we have to consider here. Vectors are equal if they have the same magnitude and direction. So let's look at A over here. So V equals W because the vectors have the same magnitude and in the same direction. So when we say magnitude, what we really mean is length. That's just a fancy word for length. They have the same length and direction. Vectors V and W and B here have the same magnitude, but they're in different directions. So notice we got V that goes kind of straight up. This one kind of goes at a different angle. So therefore, they're not equal. For C, vectors V and W have the same magnitude, but they're in opposite directions. So we always got to pay attention to where our arrow's at. If our arrows are not going in the same direction, they're not equal. Even though they look 100% equal, if they didn't have the arrows there, they would be equal. So vectors V and W for D have the same direction, but they have different magnitudes because, as we can tell, V is nowhere near the length that W is. So in every case, in order to determine if they are equal, we have to make sure that they have the same magnitude and direction. So some properties that we can deal with vectors is we can add and subtract, or we can multiply. Notice that I didn't say anything about divide because division is really multiplying by a reciprocal, so we can take care of that in our multiplication. So if we start with vector V up here on the far left, notice if we multiply it by 2, all we did was increase its length. So we just multiplied it by a scalar multiple of 2. If we had vector V, we can multiply it by 1/2 and get half the length, and we get this smaller vector. Now, when we multiply, we don't have to multiply by a straight positive number. That is why this last one is minus 3/2 times V. So what this really does is it multiplies the length by a factor of 3/2 to make it longer, and then the negative flips the direction of it. So notice we were going up with V, but negative 3/2 V, we now go down. Sometimes we might have different points and everything. We have that, in this case, initial point U, we have an initial point V, and we have a terminal point V. So we can kind of create a triangle in this sense that creates this new vector of U plus V, which it literally is U, all your components of U added to all your identical components in V to get U plus V. So when we do this, we get this nice factor here that gives us a whole different resultant. It should be a little bit smaller in length because if it wasn't, we'd have no difference than going U than V. So that's why we have this extra piece called the resultant vector. So as you know, all these are going to be worked out just the way that my PowerPoint convert in. So we're told we want to find the magnitude of u. So to find the magnitude of u, that is simply the difference of our 2 points. So this is really, so if you had u, this is our initial point, and this is our terminal point. So to find the magnitude of u, it is literally 4 minus a negative 1, which is 4 plus 1, all squared, plus 6 minus 2, all squared. So it's just like the distance formula is really what it is. So remember our distance formula, d equals the square root x2 minus x1 all squared plus y2 minus y1 all squared. That's all we got here in every case, because all these are just ordered pairs in the plane. We take our square root, so square root of 5 squared plus square root of 4 squared gets us square root of 41. We then find the magnitude of v, which is square root of 5 minus 0 squared plus 4 minus 0 all squared, which is equal to the square root of 5 squared plus 4 squared again, which is square root 41. So notice that the magnitude of v is equal to the magnitude of u. So we know they have the same length or magnitude. We know they're in the same direction because we see our arrows. So therefore, is u equal to v? Yes, because A and B are part A and part B are equal, and we're in the same direction. Now, sometimes we do have special case vectors that we can consider, and they're called the I and J unit vectors. We also have a K one if we're in three-dimensional. So vector I is the unit vector whose direction is along the positive x-axis. Vector J is the unit vector whose direction is along the positive y-axis. And so when we say unit vector, what we really mean is it has a magnitude of 1. So in other words, this point right here that we're looking at is the point 1, 0. This point up here we're looking at for the J is 0, 1. So if we took the magnitude of our vector J, we get 1. We take the magnitude of our vector I, we also get 1. So we could rewrite this point AB as multiples of our unit vectors. So our unit vector has length 1, but if we multiply by a scalar A, it no longer has length 1 anymore. And the same thing for J. If we multiply it by a unit, a scalar, or a scalar of B. So therefore, my vector, which will define the point AB, is defined by V equals AI plus BJ, where A and B are just the ordered pairs multiplied by the unit vectors. So some vector properties. So all of our properties that we talked about in terms of numbers way back in our early days of stuff, they actually hold here as well. So if U, V, and W are vectors and C and D are scalars, then the following properties are true. So for addition, U plus V equals V plus U. So we can change the order and still add and nothing changes. That's our commutative property of vector addition. Parentheses U plus V plus a W is equal to U plus parentheses of V plus W. We can change our parentheses and associate it with different things, and that's our associate property of addition. Any vector U plus the 0 vector is equal to the 0 vector plus U, which is equal to U. This is our additive identity. U plus parentheses of negative U is equal to negative U plus U, which is equal to the 0 vector, is our additive inverse. So keep in mind, In those cases, though, those are the the vectors, the zero vectors. That means all components are zero. It's like your origin, if you kind of think about it. Scalar multiplication properties. A scalar CD times U is equal to C times DU. So we're just changing parentheses. That's our associative property. A scalar C times the vector addition of U plus V, we distribute to get CU plus CV, and that's our distributive property of a scalar times two vectors. We can also have two scalars added together times a vector to get CU plus DU. This is also a distributive property. For multiplication, the 1 times U is equal to U is our multiplicative identity. 0 times U is equal to the 0 vector now, which is our multiplication property of 0. And our magnitude property here, this one's a little tricky that sometimes catches people, and it just depends on what you're given on which one's easier to do here. So the magnitude of a scalar C times a vector V is equal to the absolute value of C times the magnitude of V. So that's a property that we could use depending on what we're given. It would depend on if that is something that we want to use in that route or not. So we're told sketch each vector as a position vector and then find its magnitude. So V equals 3i plus j. So what that means is that we're going to come out 3 units to the right. We're going to go up 1 unit because our A, this is basically our A axis, and this is basically our B axis here. So A is 3 and B is 1. So we're going to the point 3, 1. So that creates this vector right here. If we find the magnitude of V, that's the square root of 3 squared plus 1 squared, which is square root of 10. So that's how long our vector is. If we have V equals negative 5j, so that basically means 0i minus 5j. So that's the point 0, negative 5. So we're going to come just straight down 5 units. The magnitude of V is the square root of 0 squared plus negative 5 squared, which is square root of 25, which is just 5. So we can tell by looking at these two, just these two examples here, that the magnitude of negative 5j is longer than the magnitude of 3i plus j. So using unit vectors. So we've already kind of done this a little bit in terms of the AI plus bj. So any vector v from the origin 0, 0 to any point AB is represented as v equals AI plus bj. And we'll talk about why we know that at the very bottom there. So the real numbers a and b are called the scalar components of v. Note that a is our horizontal component, like our x direction, and b is the vertical component, like our y direction. So the vector sum ai plus bj is called a linear combination because we're taking into consider both x and y components, or horizontal and vertical. The magnitude of v equals ai plus bj is given by magnitude of v equals square root of a squared plus b squared. Very similar to what we've already been seeing in terms of our complex numbers for magnitudes and stuff. So the reason that we know that that was a linear combination way back up there, AI plus BJ from 0, 0 to AB is the following. Vector V with initial point P1 is equal to X1, Y1, and terminal point P2 is equal to X2, Y2, is equal to the position vector given by V equals X2 minus X1 times I plus Y2 minus Y1 times J. So that's why up here, really, this is A minus 0 times I plus B minus 0 times J. So that's how it simplifies to AI plus BJ if you're starting at 0, 0. If you're starting at 0, 0, it's whatever your terminal point is there of AB. If it's any point, that's how we can represent it down here. So we're told in this example, let V be the vector from initial point P1 to terminal point P2. We want to write V in terms of I and J. So given P1 equals -1, 7, and P2 equals -7, -7, so we're going to plug it in. So we're going to do -7 minus a -1. That's how we get the +1. And then -7 minus 7 to get the next piece. So we get -7 plus 1 is -6i, and then minus 14j. So we're told let u equal 2i minus 5j, v equals -3i plus 7j, and w equals -I minus 6j. So we want to use those, depending on what we're given, to find the following. So the first one, u plus v. So when we're doing the vector addition here, we're literally adding component for component. So 2 plus -3 is the same as 2 minus 3. -5 plus 7. So we get 2 minus 3 is -I. -5 plus 7 is plus 2j. If we do u minus v, so 2 minus a -3 is 2 plus 3. And then -5 minus 7. So then we get 5i minus 12j. So for this next one, 3v minus 4w. So 3v is 3 times -3i plus 7j, which gives us -9i plus 21j. Minus, well, we'll just do 4w. So 4w is 4 times -I minus 6j. So minus 4i minus 24j. So then we're told to do 3v minus 4w. So that's going to be -9 minus a -4 times I plus 21 minus a -24 times j. So we get -5i plus 45j. For the last piece here, the magnitude of minus 2u. So there's two ways we can do this. So the first way that I did it here is I first found minus 2u, which is -4i plus 10j. So then I took the magnitude of that to get -4 squared plus 10 squared, which gives me 116. So square root of 116 is 2 root 29. If we did this by the magnitude property, this would have been the absolute value of -2 times the magnitude of u. Absolute value of -2 is 2. Magnitude of u is the square root of 2 squared plus -5 squared, which is 2 on the square root of 4 plus 25, which is 2 root 29. We still get to the same answer. It's just a matter of how you want to do it. You can multiply in first, or you can wait till the end. So on this one, we're told u equals same u's from above, just this time we want to find 3u minus the 2v minus w. So what I did here first is I made this 3u minus 2v plus w. Then we went here and we found 3 times u, so we got the 6i minus 15j. Minus 2v gave me the 6i and then the minus 14j. So these were the two vectors I needed to find because they had scalars in front of them. So then I just did all of these. So I took first component, first component, first component. So that's 6 plus 6 minus 1 times I. Then I took second component, second component, second component. So minus 14, minus 15, minus 14, minus 6. So I got 11i, and then I got minus 35j. So that's what my entire vector would equal. Several different ways you can do it, but to me, that easiest one is just build it up. Now, sometimes we're going to be asked to find a unit vector. Sometimes the vector might already be a unit vector, just might not be able to see it. Other times, it may not be a unit vector. Either way, this process will always help us determine it. So for any non-zero vector v, the vector v divided by its magnitude of v is the unit vector that has the same direction as v. And so to find this vector, divide v by its magnitude. So if we want to write a vector in terms of its magnitude and direction, let v be a non-zero vector. If theta is the direction angle measured from the positive x-axis to v, then the vector can be expressed in terms of its magnitude and direction angle as v equals magnitude of v cosine theta times I plus magnitude of v times sine of theta times j. So going back up here for a second to talk about this unit vector. So every time we would want to find the magnitude of v first. If this equals 1, then this is just equal to v. If the magnitude of v does not equal 1, then we need to go ahead and do our division. So like right here, it says find the unit vector that has the same direction as the vector v. All right, so 4i minus 2j. So we find its magnitude. So square root of 4 squared plus negative 2 squared gets us square root of 16 plus 4 is square root of 20, which breaks down to 2 root 5. So this right here told me that this is not a unit vector. So we need to divide. So we're literally dividing every single term by 2 root 5. So when we divide, we get 4 over 2 root 5 times I minus 2 over 2 root 5 times j, which is equal to 2 over root 5 times I minus 1 over root 5 times j. So our original vector was the point 4, negative 2. Originally, our vector was something like this. If we look at our new vector, 2 divided by square root of 5 minus 1 over root 5. So if we were to approximate these two values, this would be 0.89 times I minus 0.45 times j. So 0.89 and negative 0.45 gives me a vector. It's in the same direction, but it's a lot shorter than the one that we have here. So all we did was find a scalar multiple of our original vector there. So we're told write the vector v whose magnitude and direction angle are given in terms of I and j. So we're told magnitude of v is 10, theta is equal to 330. So V equals 10 cosine 330I plus 10 sine 330J. Cosine of 330 is equal to square root of 3 over 2. And sine of 330 is equal to negative 1/2. So 5 root 3I minus 5J would be our answer. We'll always go ahead and simplify this piece right here. Do not leave it as sines and cosines. So a vector that represents a push or pull of some type is called a force vector. So if we have a force 1 pulling 10 pounds at an angle of 20 degrees off the y, so about 70 degrees. And if we have a force 2 pulling 30 pounds at about 65 degrees, then that's what we can find. We are looking for this resultant vector right here. So when we do that, anytime we're talking theta, we're actually talking theta off of the y-axis, not off of our standard piece here. So notice that force 1 comes 20 degrees off of the top here, and then 65 degrees comes here. Yes, I know I quoted them the other way, but understand this is off of the y-axis because that's the direction that we're pulling it. So now we're going to get a little in depth here on some word problem examples. Oops, sorry about that. So the magnitude and direction of two forces acting on an object are 70 pounds, south 56 degrees east, and 50 pounds at north 72 degrees east, respectively. Find the magnitude to the nearest hundredth of a pound and the direction angle to the nearest tenth of a degree of the resultant force. So let's just do a quick little drawing just to show what's going on here. So two forces acting on object are 70 pounds at south 56 degrees east and then 50 pounds at north 72 degrees east. So if we apply what we call as the parallelogram rule, oh, come on, I didn't want to do that. Then we can take our original vector that's 50 and we can put it down here. We can take our original vector that was 70 and we can put it here. So what we're actually looking for is this unknown vector right here, this green vector. So what we really have to figure out here is we got to think about this. We always draw our components down to the X and Y axis. So we need to figure out in each case what our X component is and then our Y component. So we need these two here. And then I also need this one here. So for my force 1, which was my 70 pounds force, so this is F1 and this is F2. And I'll call this F3. So for force 1, it's 70 times cosine of 90 minus 56I plus 70 times sine of 90 minus 56J. That gives me 58.03I minus 39.14J when we pull up our calculators. For my second force, 50 cosine 90 minus 72I plus 50 sine 90 minus 72J gives me 47.55I plus 15.45J. Notice these put us in the exact quadrants we need to be because this is a quadrant 4 and this is a quadrant 1 in terms of X, Y, or A, B values there. So my resultant force F, also known as F3 in my case here, is going to be F1 plus F2. So we're going to add our X components, or our I components, I should say. And I'm going to add my J components. So I get 105.581 or 58I minus 23.69J. That puts me in quadrant 4. So that's something to keep in mind because of my X being positive and my Y being negative. So the magnitude of it is the square root of 105.58 squared plus 23.69 squared, which gives us a nice number of 11, square root of 11,708.3525, which is approximately 108.21 is the magnitude. It wants it to the nearest hundredth. And we also need the direction angle. So sine of theta in this case is going to be B, which is negative 23.69 divided by magnitude of F. So negative 23.69 divided by 108.86. Actually, that should not be 86. That should be a 0.21. Which when we do that, we do our inverse sine there. We get theta to be negative 12.65 degrees. We don't want a negative theta, so we need to add 360 to that. So plus 360 gives us the 347.4. So that would be this entire angle here. So if we really were writing it back in terms of the same thing, so we would have to take 360 minus our 347.4. I'm sorry, not 347.4. 360 minus, sorry, not 360, 347.4 that we're given minus 270. So really this would be a south 77.4 east would be my direction in terms of that. So depending on how it's looking for it. So if it just wants the angle of my vector, then it's 347.4. If it wants it in terms of just like it was given to us, it's south 77.4 degrees east. So we got several little questions that go along with these on the next couple slides here. So first, express the given vector in terms of I and j. If possible, give exact values. If not, round to the nearest 10. A plane with an airspeed of 490 miles per hour is flying in the direction north 25 degrees east. So, north 25 degrees east with a magnitude, so 490 is my magnitude. So in other words, this angle is 65. So 490 cosine 65 times I plus 490 sine 65 times J is equal to 207.1 I plus 444.1 J. So this one right here gives us several different things to work with. So express V and W in terms of their magnitudes and direction angles. So we're told that a plane is flying at 180 miles per hour on a bearing of north 50 degrees east. So we know that our angle here is 40. So for my vector v, this is going to be, vector v is going to be sorry about that, I was looking just in the wrong way. So vector v is going to be, this one has a magnitude of 180. I was missing that right there. I was looking down here at this wind speed and seeing it was 40 as well. So v is equal to 180 cosine of 40 degrees times I plus 180 sine 40j. And w, since it's along my x-axis, it's going to have an angle of 0. It's got a wind speed of 40 miles an hour. So 40 times cosine of 0, I plus 40 times sine of j. Now, if we want our resultant vector of v plus w, we're going to add our components here. So 180 cosine 40 plus 40 cosine 0, all times I, plus 180 sine 40 plus 40 sine 0, all times j. So that gives us 177.89 times I plus 115.70 times j is the v plus w resultant vector here. So 177.89 I plus 115.70 times j. So same example, still going with it. Find the magnitude of v plus w, which is given to our ground speed, what we can measure our ground speed at. So that's going to give us the square root of 177.89 squared plus 115.7 squared, which when we round to the nearest mile per hour gives us 212 miles per hour. So the direction angle of v plus w gives the plane's true course relative to the ground. What is the plane's true bearing? So cosine of theta is equal to a over magnitude of v plus w. So that's 177.89 over 212, which gives us that this angle here for v plus w is 33 degrees. Now keep in mind here that to find our direction angle here, we can use cosine theta equals a over the magnitude of our vector. I'm just going to use u as a generic vector. Or we could do sine of theta equals b over the magnitude of a vector u. Both of these give our direction angle. It does not matter which one we use. They both end up with the same exact thing in the end. So that's what we need to start our talk about vectors on, and then we will continue on in the next lesson as well.